Oops. Okay. Well, let me go back to this. Okay, so as I was saying, oh shucks. As I was saying, we're going to do the next example here, where they gave us the composition data, and you're to determine the empirical formula. So let me go here, and let me. Okay, so let me clean this up here. All right, so the question says that we're dealing with a compound known as diethylene glycol, and it gives you some composition data here. And if you remember, based on the examples that we have looked at so far, the first step would be simply to assume that the percentages would represent the mass in grams present in 100 grams of the substance. So these are the masses for the different elements. For carbon, it's going to be 45.27 grams. For hydrogen, it's 9.50 grams. And for oxygen, it is 45.23 grams. And then what we do next, as we did before, in the next row, is that we're going to convert these to moles. So 45.22 grams multiplied by, in the case of carbon, 1 mole over 12.01 grams. In the case of hydrogen, it's 9.50 grams multiplied by 1 mole over 1.008 grams. And in the case of oxygen, it's 45.23 grams multiplied by 1 mole over 16.00 grams. Okay, so I left my calculator. Hold on, there should be a calculator here. Hold on. Okay, so in the case of carbon, I'm going to multiply or divide 45.27 by 2.01. And according to my calculations, this works out to be equal to, when rounded off to 4 sig figs, 3.769. 3.769 moles. And I'm going to do the same thing for the hydrogen. So I'm going to multiply 9.50, or divide by, I should say, 1.008. And that will be equal to 9.42. So I'm going to write down 9.42 moles here. And then finally, in the case of oxygen, it's going to be 45.23 divided by 16.00. And that works out to be, according to my calculations, 2.827, all right? Okay, so the next step, if you recall, is that we compare these three numbers and we decide which one is the lowest, which is this one right here, and we divide right through by that number. So in the next row, we're going to divide right through by 2.827 moles. So this you're going to have 3.769 moles divided by 2.827 moles. Here we're going to have 9.42 moles divided by 2.827 moles. And this divided by itself will give you 1, all right? So let's work out these two here. So for the first one, I'm going to work out 3.769 0.769 divided by 2.827. And when I work that out, the answer I got here will be 1.333. All right. And then in the case of hydrogen, I'm going to divide 9.42 by the same number, 2.827. And that gives us, according to my calculation, 3 that's equal to 3.33. And again, this is just one. Let me make sure that that is seen as one. Okay, now at this juncture, you'll notice that we have a recurring 3 after the decimal point here and here. Now these two numbers, if you remember what we did the last time, we basically rounded off to the nearest integer in the last examples. However, in this case, we can't do that because these two numbers here are too far from the nearest integer to be rounded off simply like that. However, what we need to do is to basically multiply right through by a certain number, which would convert all these numbers, this one and this one, into integers. And you'll notice, as I said before, there's a recurring 3 after the decimal point here and also here. So what that suggests is that if you multiply right through by 3, you'll convert these numbers into integers. So as far as the 1.33 is concerned,
4, 10, and 3?
Yes. Yes, so yeah, you're right. So in actual fact, this would be 3.999, which is approximately 4. And then this one here, when you multiply 3.33 by 3, you're going to get 9.99, which is approximately 10. And of course, this number here, when you multiply by 3, will give you 3. So therefore, in this case, the empirical formula is equal to C4H10 H10O3. And that's basically how you do this sort of problem, all right? So that's basically how this is done. And let me just say that there are some instances where you might end up with, instead of a 3, recurring 3 after the decimal point, you might end up with, in fact, let me, is it okay to erase this?
I'm good. Not sure about the other two.
Okay, I'm going to assume that it's okay. You can look it up on the video in any case, because I just want to show you something here. If there is a recurring, as we saw in the example we just did, if there's a recurring 3 after the decimal point, then we multiply everything by 3 at that stage. If there's a recurring 6 after the decimal point, we multiply by 3 again. If there's a 5 after the decimal point, we multiply by 2. If there is a 0.25 or 25 after the decimal point, we multiply by 4. If there is 0.75, we multiply by 4. If there's a recurring 1 after the decimal point, we multiply by 9. And I think that's all I can think of right now. In all other cases, okay, why did that happen? In all other cases, you may just need to do some trial and error in order to figure out what to multiply by in order to convert the given value into an integer. So it all depends. You'll notice, for example, when you multiply 0.666 by 3, you're going to get 2. When you multiply, here, when you multiply 0.33 by 3, you're going to get 1. If you multiply 0.5 by 2, you're going to get 1. If you multiply 0.25 by 4, you're going to get 1. If you multiply 0.75 by 4, you're going to get integer 3. And if you multiply 0.11 by 9, you're going to get 10. All right.
Wouldn't that actually just be 1?
I mean 1, sorry. You're right, yeah. 1. So that's basically what you need to do at that stage. All right.
Just going for the lowest whole number, more or less.
Exactly. Right. Exactly. Exactly. Okay. So any questions about that example, even though I erased it already? Any questions? Okay. So moving along, let's talk about a topic which I doubt very seriously you would have met before in your introductory chemistry courses. So this has to do with what we call elemental analysis. And what we're talking about here, oh, by the way, let me turn on my video so you know that I'm not sleeping or I'm still alive. So what we're talking about here is how do we get the percentage data that we were using in the previous examples. Now, this particular method is one that applies only for simple organic compounds. In other words, compounds that contain carbon, hydrogen, and maybe oxygen, and maybe some other non-metallic elements, all right? So the method that I'm about to describe is the method that is used to determine the elemental composition for such compounds, all right? And basically, this is based on burning the compound and collecting the products. Now, you should have learned in your previous chemistry courses or course, introductory chemistry or high school chemistry, you should have learned that an organic compound, when it's burnt, it undergoes what we call combustion. And the products is going to be carbon dioxide and water if the combustion is complete. Now, if there are other elements, you might end up with some other products, but you will end up definitely with carbon dioxide and water, all right? So the concept that is involved in terms of the elemental analysis is that we somehow collect the products, this carbon dioxide and water, and then we weigh them. And based on the masses of those products, we can work our way backwards to determine the composition of the different elements present in the original organic compound, all right? So that's basically the basis for this type of analysis, all right? Now, the next slide shows you a schematic representation of how this is carried out. So you'll notice that you have a series of chambers that are connected to each other, and each chamber has different items. The first one has the compound that you're analyzing, right? So this would be your organic compound. And then here you have a substance known as magnesium perchlorate, and you have sodium hydroxide in the third chamber. And you'll notice that oxygen is being forced into this chamber here, which is actually a furnace, right? So basically your sample here will be heated. And as I said before, when your organic compound is heated, it's going to produce carbon dioxide and water. So basically, carbon dioxide and water would be delivered from the furnace after the combustion of the material here and led into the chamber containing the magnesium perchlorate. Now, the thing about magnesium perchlorate is that it is very, what's the word? It is very, oh gosh, I forgot the word that is used for substances that absorb water from.
Absorbent?
It's absorbent, but there's another term. But anyway, it absorbs water, all right? So basically, of the two products that would be emerging from the furnace here, it is the water that will be absorbed by the magnesium perchlorate, right? So the precaution that you'd have to take at this point is that you have enough magnesium perchlorate here to absorb all the water that is produced from the sample. So basically, after all the water is absorbed here, that means that the only product that should be emerging from it would be the carbon dioxide. And that carbon dioxide will be led into the chamber containing the sodium hydroxide. And the sodium hydroxide, of course, will absorb the carbon dioxide because the sodium hydroxide is basic and the carbon dioxide is an acidic gas, all right? So basically, those are the two products that would be absorbed in each chamber, right? So basically, the only thing that would be emerging from this chamber here would be the heat that is generated from the reaction. Now, the way this works, the way we actually do this experiment is that we weigh the water, we weigh the magnesium perchlorate and the sodium hydroxide before you start the reaction. And then after the reaction takes place, you separate the different chambers and then you weigh the magnesium perchlorate and the sodium hydroxide afterwards. And the increase in masses of each of these would reflect the masses of the water and the carbon dioxide respectively for the magnesium perchlorate and the sodium hydroxide. And then, as I said before, based on the masses of the water and the carbon dioxide, you can work backwards to determine the mass of the original compound. So that's basically what is involved in this sort of elemental analysis, all right? So as we said before, the water is absorbed by the magnesium perchlorate, and the sodium hydroxide will absorb the carbon dioxide. And the difference in the masses before and after the reaction would give you the masses of the water and carbon dioxide that is produced as a result of burning your original compound. Okay, so that's basically an overview of how this type of analysis is conducted. So this is an actual example of such a combustion analysis type problem. So let me go to my writing application here. And let me, okay, what's going on here? Okay, so let me go back to the question so you can get a feel for what the question is asking for. So the question is talking about a substance known as menthol, which is what we're analyzing. And it is composed of carbon, hydrogen, and oxygen. And the question says a 0.1005 gram sample of menthol is combusted, producing 0.2829 grams of carbon dioxide and 0.1159 grams of water. So the question is asking, what is the empirical formula for the menthol, all right? So let me go to my writing tablet here. And first thing I'm going to do is start off with the mass of the carbon dioxide, which is 0.2829 grams of CO2. And what we need to do is find the mass in grams of carbon in that carbon dioxide. So we start off with the 0.2829 grams of CO2, and we multiply that by 1 mole of CO2. And the molar mass of CO2, of course, you can go to the periodic table and add up the molar masses of carbon and the 2 oxygens, and you're going to get 44.01 grams of CO2. The next step is to determine the moles of carbon dioxide. And based on the formula, we know that for every mole of carbon dioxide, you have 1 mole of carbon, right? So down here, we're going to put 1 mole of CO2, and up here, we're going to put 1 mole of carbon. And up to this point, we would have determined the moles of carbon, but the next step is necessary because we need to find the mass of carbon in the given mass of carbon dioxide. And to do that, we have to multiply the moles of carbon by the molar mass. So you're going to have the molar mass, which is 12.01 grams of carbon for every 1 mole of carbon, so that this will cancel out with this. So at this juncture, what you'll get would be the grams of carbon, all right? So let me do my calculation here. So in the case of, we're going to multiply 0.2829 multiply by, or actually divide by, let me back up here, do this again, 0.2829 divided by 44.01, and then multiply by 12.01. And according to my calculation, this works out to be equal to 0. How many sig figs? 4 sig figs. 0.02184 grams. Let me do this again just to be sure. I think I may have made an error. 0.2829 divided by 44.01.
That gives me, so the division part gives me
Okay.
0.006428.
No, actually, the answer is, let me erase this here. Yeah, I made a mistake. I don't know what the mistake was, but I knew something was off. When I redid it, this is the answer I got. Oops, let me go back to my pen function. So this is the answer I got. 0.07720 grams.
Yeah, that's what I got after I did the multiplication. The number I was reading off was just doing the division part.
Oh, okay. Yeah. All right. So so that's as far as the carbon is concerned. Now, the next thing we need to do is determine the number of grams of hydrogen. So we're going to start off with a 0.1159 grams of H2O multiplied by 1 mole of H2O. And down here would be the molar mass of water. So again, you'd have to go to the periodic table and add up the molar masses of 2 hydrogens and 1 oxygen. And if you do that, you're going to end up with 18.02 grams of H2O. The next step is where students very often slip up and screw up their calculation. If you recall, at this juncture here, we said that for every 1 mole of carbon dioxide, there's 1 mole of H2O, right? And that's because based on the formula, there's only 1 carbon atom per molecule of carbon dioxide. In the case of water, there are 2 molecules of hydrogen or 2 atoms of hydrogen for every molecule of oxygen. So therefore, the conversion factor that we're going to use here is that you're going to have 1 mole of H2O down here. And up here, you're going to have 2 moles of hydrogen. So please make a note of that. For every 1 mole of water, you're going to have 2 moles of hydrogen. I can't tell you how many times students in the past have made the error of putting a 1 here instead of a 2, all right? So it's 2 moles of hydrogen for every 1 mole of water, and that's because of the subscript 2 here in the formula for water. The final step in this process here is where we put the molar mass of hydrogen. We multiply by 1.008 grams of hydrogen for every 1 mole of hydrogen, all right? And then we work that out. So let me do my calculation here. So this would be 0.1159 divided by 18.02 equal, and then multiply by 2, and then multiply by 1.008 grams. And according to my calculations, this works out to be equal to 0.0, okay, what's this? 4 sig fig, so 0.0121297 grams of hydrogen, okay? All right, so far so good. We have determined the mass of carbon and we have determined the mass of hydrogen. But there's a third element, because if you read the question, it says the compound consists of carbon, hydrogen, and oxygen. So the question now becomes, how do we determine the mass of the oxygen? Well, it's very simple actually, because the question also gave us the total mass of the compound. So if there are only 3 elements present and we know the mass of 2 of them, then all we have to do is subtract the total mass of those 2 elements from the mass of the compound, and that will give you the mass of the oxygen. So the way I'm going to set this up over here is that I'm going to start off by saying the mass of oxygen will be equal to the total mass of the compound, which is 0.1005 grams, minus the sum total of the masses of the carbon and hydrogen, which we have here and here. So in parentheses, we're going to put 0.07720 grams plus 0.01297 grams And then we work this out. So what I'm going to do is work out what's in the parentheses first. 0.07720. And I'm going to add that to 0.01297 and then press equal. And then I'm going to subtract from that 0.1005. And according to my calculations, this works out to be equal to 0. Let me see here, 0.01033 grams. So that would be the mass of the oxygen. All right. Okay, so let me write this down here because I have to erase and I don't have any paper here. Okay, I do have paper. All right, so what I'm going to do is just write down here the masses because I have to erase this on the screen. I'm just going to write down the masses of the carbon, hydrogen, and oxygen. So the mass of the oxygen, the carbon is 0.07720 grams. The mass of the hydrogen is 0.01297 grams, and the mass of the oxygen is 0.01033 grams. Okay, so let me get rid of this here. And what I'm going to do next, because remember, the aim of this exercise is to determine the empirical formula. So what I'm going to do next is to set up my table, just like I did before. And this time, instead of the percentages, I'm just going to put the actual masses that we just calculated for the carbon, oxygen, and hydrogen. Okay, so mass. So we calculated the mass for the carbon as being equal to 0.07720 grams. For hydrogen, it is 0.01297 grams, 1297 grams. And for oxygen, we calculated 0.01033 grams, all right? And basically we follow the same blueprint as we did for the previous examples that we worked. So let's get you guys involved. What would be the next step based on what we did before? What would be the next step?
Try to get them as close to a whole number as possible.
Nope. That's way down. That's almost the last step. What you just said. But there are a couple of steps before. So what's the next step?
Sorry, I'm still very tired. Try to find how that's the way to say this.
Try to find the what? Convert to moles. Okay. That's what you said, right?
Yeah.
Okay. So how would we do that for the carbon?
Well, you take your grams, compare it to.
What do we multiply this by?
One over 12.01, I think.
Right. 1 mole over 12.01 grams. Don't forget the unit, folks. Yeah. I don't know if anybody told you guys, but I'm a stickler for units. So make sure you include your units as a part of the calculation. Okay, what about hydrogen? We take the 0.01297 grams and we multiply that by what?
That would be 1 mole over 1.008
0.008 grams, yep. And then for the oxygen, 0.033 grams. What do we multiply that by?
See, I think 16.01 was oxygen. So 1 mole over 16.01.
We're
grams.
16.00 actually.
Sorry, yeah.
Okay. All right. So let's work out each of these. So for the first one, it's going to be 0.07720 divided by 12.01, 12.01. And according to my calculations, this works out to be equal to 0.006428 moles. And then in the case of hydrogen, it's going to be 0.01297 divided by 1.008. And according to my and by the way, folks, I don't know if I've told you this before, but whenever I'm doing these calculations, you should do them along with me because I could be leading you guys astray. So do the calculations along with me so that, you know, we are all on the same page. According to my calculation, this gives 0.01287. So just make sure you do the calculations and confirm what I'm doing is correct, all right? And then for oxygen, it's 0.01033 divided by 16.00. And according to my calculations, this works out to be equal to 0.000, and then you have 6456 moles, all right?
Yep.
Okay, so those are the mole values. So do you remember what the next step is? Somebody said it earlier. Well, no, I don't think somebody said it earlier, come to think of it. So what's the next step?
Find the smallest and then divide across the board by that.
Okay, so the smallest of these three values would be this one right here, right?
Yep.
So we know that when that is divided by itself, it's going to give you 1, right? Now, as far as the carbon is concerned, when we divide 0.006428 moles by 0.0006456 moles. Okay, so what does that give? 0.00648.
I'm getting 9.957.
That sounds right. 0.00646. 9.9. Oh gosh, where's my stylus? Okay. So yeah, what I got is round off to 4 sig figs, 9.957. That's what you said, right?
Yes.
Okay, cool. And then we do the same thing here, 0.01287 moles divided by, again, 0.0006456 moles.
I'm getting 19.93.
287 divided by 0.0006456. You said 19.93, right?
Yep.
Okay, that's what I got too. Oh, by the way, this should not be moles because the moles will cancel out. So, okay. And obviously, what that means is that this will be rounded up to 10, and this will be rounded up to 20, and this is still 1. So therefore, the empirical formula, where am I going to squeeze? Let me squeeze it up here. The empirical formula for this compound would be C10H20O. And that would be how you do that particular problem, all right? So as you can see, this one is a bit more complicated than the other examples because what you'd have to do is first determine the masses from the data that is given in the question. Determine the masses of the different elements present, right? And then once you do that, once you get the masses of the different elements, then you basically do the same thing as we did in the previous examples, where you convert the masses to moles, then you find the simplest ratio, and then you round off if necessary, or you may take it the next step where you have to multiply by a certain integer to get all those numbers converted to integers. And then based on that, you can determine the empirical formula, all right? Okay, any questions about this example? Any questions? Any questions? Okay, so moving along, let's talk about stoichiometry. Again, this is something you should have met in your high school or introductory chemistry course. Stoichiometry is that area of chemistry, and I think I said so at the introduction of this chapter, where we're looking at the quantitative relationships between different substances, all right? Before we can do such calculations, however, you have to know how to write down what is called a balanced equation. Of course, we know that for any equation that you're going to write to represent a reaction, on the left side of the equation, you're going to have the reactants, the formula for the reactants, and then you have your arrow pointing to the right, and then on the right side of the equation, you're going to have the formula for the products, all right? So, as stated here, the chemical equation is a shortened description of a chemical reaction, and we use symbols and formulas to represent all the substances involved in the reaction. As we said before, the substances on the left would be the reactants, and the substances on the right would be the products. And of course, we use a plus sign to separate between each reactant and product on either side of the equation. And of course, the arrow points towards the products from the reactants, all right? So basically, the arrow gives you the direction of the reactants or the reaction from the reactants to the products. So some notations that are normally included in a chemical equation. And again, these you should be familiar with. You have G for gas, L for liquid, S for solid, and AQ. And these are normally written right beside the formulas for the different substances to indicate their states, right? So that just basically provides you some more information about the states of the substances involved in the reaction. You may see some extra notation such as triangle, which basically represents heat, or in some cases, you might see the actual temperature or the actual pressure, or they might include other information about the conditions of the reactions, like whether or not a catalyst is present, etc. All right, so those are the other things that you might see in addition to the state symbols that is mentioned up here. All right, okay, so let's consider the simple example of the reaction where water is formed from hydrogen and oxygen, right? Now, in order for this equation to represent accurately what is happening, it has to obey the law of conservation of mass. And if you remember the law of conservation of mass, it says that basically in a chemical reaction, matter is conserved. In other words, the total mass of the reactants involved in the reaction would be equal to the total mass of the products that are produced in the reaction. And we know that according to Dalton's theory, which explains this particular law, Dalton's theory says that basically atoms are not created nor destroyed in a chemical reaction. Basically, instead, you have bond breaking and bond formation, rearrangement of the atoms to form new products, all right? So that must be reflected in an equation if it is to accurately represent the changes to take place. In other words, the equations must be balanced. In other words, the equation must represent what we just said about Dalton's theory, that the number of atoms created, or I should say the number of atoms of each element should be the same on both sides. No atoms will be created nor destroyed. Okay, so how do we do that? Well, we have to make sure that we do what we call chemical bookkeeping. And we look at, in this particular case, we start off by looking at the hydrogen, and you'll notice that there are 2 atoms of hydrogen on the left, same thing as on the right. So therefore, as far as the hydrogen atoms are concerned, they are balanced, all right? But the oxygens are not, because you'll notice that you have 2 oxygen atoms on the left, but only 1 on the right. So what do we do in order to balance the oxygens? Well, let me just show you what should not be done, which would be totally incorrect. I'm using this diagram right here. So you'll notice that this is the unbalanced equation firstly, all right? And this is an incorrect attempt at balancing the equation. So what this person did was simply add an oxygen to the right side in order to balance the oxygens. That is a no-no. You cannot do that when you're balancing an equation. You cannot just simply add another atom to either side in order to achieve the balance of the oxygen. Another big no-no is changing the formula of a substance, in this case, the water. What this person tried to do is change the formula of water to hydrogen peroxide by putting a coefficient of, not a coefficient, I'm sorry, a subscript of 2 down here, all right? Again, that is incorrect, all right? What you should modify in an attempt to balance the equation are the coefficients, the numbers that are placed in front of the substances or in front of the formulas in the equation. And this is the correct way of doing it in the case of this equation. Basically what this person did was place a 2 in front of the water here to balance the oxygens, but that would change the number of hydrogens on this side, which means that you'll place a 2 in front of the H2 here to balance the hydrogens, all right? And therefore you achieve the balance of all the atoms in this equation, all right? So basically, when you're balancing equations, you don't change any of the subscripts. You don't simply add any atom to either side. What you modify or change would be the coefficients, right? And, you know, based on past experience, you should know that, you know, some of these cases is basically a sort of trial and error kind of thing, where you try one number and then you make adjustments on the other side and you go back and forth. In fact, let us do a couple of examples so that you'll be reminded of how to balance an equation. So let's say you're given, okay, what's going on here? Okay, so let's say you're given N2 plus H2 to give N H3. So how would you go about balancing this equation? Anybody? You should be able to do this one.
I mean, you can like count how many of each thing you have.
Okay, so let's start off with the nitrogen. How many nitrogens do you have on the left side?
2.
And how many do you have on the right side?
1.
Okay, so how would you make sure that the nitrogens are balanced?
Put a coefficient of 2 on the right side.
Okay, so you put a coefficient of 2 in front of the ammonia on the right side. Okay. What about the hydrogens? How many hydrogens do we have on the left side?
2.
And how many hydrogens do we have on the right side?
6.
Okay, so how would you balance the hydrogens?
Put a coefficient of 3 on the left side.
Okay, very good. So that's basically how you'd balance that particular equation, all right? Okay, very good. Relatively simple example. Let's try one that's a bit more complex. Suppose you're given this. To form NO2 plus H2O plus O2. Okay, so how would you balance this equation? Let's start with the hydrogens. How many hydrogens do we have on the left side?
1.
Okay, so we have 1 on the left side. How many do we have on the right side?
2.
Okay, so how would you balance the hydrogens?
Put a coefficient of 2 on the left side.
Okay, very good. Okay, let's look at the nitrogens. How many nitrogens do we have on the left side?
2.
Okay, and how many do we have on the right side?
1.
Okay, so to balance the nitrogens, what do we do?
Put a 2 on the NO2.
Okay, very good. Whoops, 2. Okay, so that leaves us now with the oxygens. How many oxygens do we have total on the left side?
6.
6 oxygens, all right? How many oxygens do we have on the right side?
7.
You sure? Let me see.
Oh,
4
8. 8.
plus 1, 5. You're right, actually, 7, yeah.
Oh, okay.
4 plus 1, 5 plus 2, 7. So we have
Yeah.
7 oxygens on the right side and 6 oxygens on the left side. Now, can anyone suggest a way of ensuring that the number of oxygens are the same on both sides? How do we balance the oxygens? Anybody? We have 6 oxygens on the left and we have 7 oxygens on the right. So how would you balance the oxygens? All right, tell you what, since it's now 10:51, I'm going to take a break. You may want to continue thinking about this, and we're going to resume at 11 and finish this particular example, all right? I'll be back shortly.
Make me in your
Okay, can you all hear me?
Yeah.
Yeah.
Okay, so have you figured out how we balance this particular equation? Or more specifically, how do we balance the oxygens?
Yeah. Well, I put a 2 on the H2O.
Mhm. So you're saying replace the 2, hold on. So replace the 2 with a 4. Wait, I'm sorry. You said H2O, I'm sorry.
Yeah.
So you put a 2 for the H2O, okay. I'm sorry, let me erase this here. What else?
And then I changed the on the left side. I think I
Uh-huh.
changed the 2 to a 4.
Okay, so 4 for the HNO3. Okay,
And then on the NO2, I put a 4.
okay, so 4 NO2. All right,
And then on the O2, I just left it as 1.
okay. And that indeed would be the correct answer. Now, for some of you who may have some difficulty understand how we come by this, what I would suggest to do is that in order to balance the oxygens on either side, I would put a coefficient of half here for the oxygen, all right? Because by doing this, you now have the number of oxygen atoms on the left side being equal to 6, right? 4 plus 1, 5 plus half of 2, which is 1, would give you 6, which balances with the 6 oxygens on the left side. And then, because you need to have integers for coefficients, you multiply the entire equation by 2, right? So 2 times 2 gives you 4. 2 times 2 gives you 4 here. 2 times 1 gives you 2 here. And 2 times a half gives you 1 here, all right? What's going on with this? 1 here, all right? And that's it. That's basically how you balance that equation, all right? Okay, let's do 1 or 2 more examples and then we'll move on to other things. Suppose you're given C6H12O6 plus O2 to give you CO2 plus H2O. So how would you balance this equation? Any ideas? Let's start with the carbon. How would you balance the carbons?
I think you got to put a 3 to the right side.
A 3 here.
Yeah, that'll give you 6.
It would give you 6 oxygens, but not 6 carbons.
Okay.
So I wouldn't agree with that. Let me erase it. Oops. What is going on with this here? Okay. Okay, so what would you put beside the CO2? Anybody?
Oh, 6.
Okay, very good. A 6. Okay, so far so good. What about the hydrogens? How would you balance the hydrogens? You have 12 on the left side total, and you have 2 here on the right side. So what would you do?
Is it another 6?
Exactly. And then what do we do about the oxygens? Now, in the case of oxygen, we have 6, we have 6 plus 2 on the left side. And on the right side, we have 12 plus 6, 18 oxygens. So what would you do? Well, how would you balance the oxygens?
Put a 6 on the O2 on the left side.
Put a 6 on the O2 here. And yes, I would agree with that. And therefore, the equation is now balanced. Okay, so, this skill of balancing equation is very important. You're going to see that a lot of stoichiometric problems, well, I would say all stoichiometric problems would have to, you'd have to start with a balanced equation in order to solve these kind of problems. And in some cases, you may be given the equation to balance. In other words, you're given an unbalanced equation and you're asked to balance it. In other cases, you may be given a description of the reaction in words. In that case, you'd have to figure out what the products and reactants are. And again, you'd have to balance it. But you cannot solve any stoichiometric type problems without a balanced equation. And therefore, it's a very important skill that you need to master in order to solve stoichiometric type problems, as you're going to see shortly. Okay, so let's move along to a discussion of the related topic of stoichiometric equivalence. So, and again, this underscores the importance of having a balanced equation, because what you'll find is that the coefficients from the balanced equation would basically represent the mole ratios between the different substances involved, right? And you can basically express those ratios as conversion factors. So for example, in the reaction of hydrogen, let me write it up here, hold on. Sorry about that. So remember the equation, which is H2, two of them, plus O2 to give 2H2O, all right? So these coefficients, the 2 here, the one that is understood to be here, and this 2 here, would represent the mole ratios of the different substances involved. So as you can see down here, we can express the equivalences between different substances. For example, between the hydrogen and oxygen, that's a 2-to-1 mole ratio based on the coefficients for both of them. Between the hydrogen and the water, that's a 2-to-2 ratio. And between the oxygen and the water, that would be a 1-to-2. So this is an error right here. This should be a 2 here, all right? And you can express each of these as conversion factors. So for example, in the case of the relationship between the hydrogen and the oxygen, you can express it like this: 2 moles of hydrogen over 1 mole of oxygen, or the other way around. And which one you're going to use is dependent on the nature of the question, what you're trying to determine, all right, as you're going to see in some examples we're going to look at. Okay, in fact, let me see here. Let me try to find an example based on what we just covered. So I'm going to do a Google search of stoichiometric problems. Let's see here. Let me try this one here. Oh, well, they actually give you the work solutions. I don't like doing that. I prefer to work it out. Let me see what this one is saying. And I cannot write on this. Ah, I hate when this happens. All right, you know what? What shall I do? What shall I do? Let me see, let me see, let me see. Let me go back here. Okay, I'm sorry about this, folks. I should have actually, let me see what this gives. Okay, let me see. I'm just going to, okay, what I'm going to do is copy this equation here. Hope it comes out okay when I try to post it or paste it here. Okay, I guess I cannot paste it here. So let me go to, okay, let's see if this would work. Okay, so this is the equation here. And what I'm going to do is go back here and copy this part here. And let me paste it here. Okay. So in this case here, you're given the balance equation. And the question is asking how many grams of NO are produced when 25 moles of oxygen reacts with an excess of ammonia. So the way we set this up is we start off with the 25 moles of oxygen. And the first thing I would do is write down a conversion factor which relates the moles of oxygen to the moles of NO, right? And as you can see, that's a 5-to-4 mole ratio. So down here, I'm going to put 5 moles of oxygen, and up here, I'm going to put 4 moles of NO, so that this will cancel with this. And then the next step is where we convert the moles of NO to grams of NO. In other words, we need a molar mass. So down here, I'm going to put 1 mole of NO, and the molar mass of NO is, nitrogen is 14.01, and oxygen is 16.00. So that would give you 30.01 grams, and that would go up here, 30.01 grams of NO. And then this will cancel with this. And all we have to do now is the number crunching, where we multiply 25 by 4, and then we divide by 5, and then we multiply by 30.01. And according to my calculations, this works out to be equal to, you have to round off to 2 sig figs. So this would be 6.0 times 10 to the 2 grams of NO. And that's how you do that. So that's a relatively simple example, but I thought it was important that I show you how to do this. And in fact, this is something you should have learned in your introductory chemistry. So this should come as no surprise to you. Okay. Any questions about that example? All right, now let's talk about this concept of limiting reactants. Again, this is something that you should have met before. Very often in practice, when you're doing a chemical reaction, very often in order to ensure that you get a decent amount of product, you have to make sure that the amount of one or more reactants is actually in excess. That's just simply how things happen when you're doing reactions to produce something that you want to produce, all right? So this basically is where the concept of limiting reactants or limiting reagents come into play. Now, to illustrate this concept, I'm going to use the example that you see on the screen. Let's say that you're given a task of preparing lunches or a packaged meal. And the formula that you're going to use in order to come up with a packaged meal is that you're going to have 1 sandwich, 2 cookies, and an orange, all right? So this is basically the form of a chemical equation. 1 sandwich, 2 cookies, and 1 orange would give you 1 packaged meal, all right? So what if you have 11 sandwiches, 16 cookies, and 10 oranges, all right? How many packaged meals can you get from these items based on the equation that you have here, all right? Now, if you look at things from the standpoint of the sandwiches, right? It's a 1-to-2 ratio between the sandwich and the cookies. So therefore, 11 sandwiches would require 22 cookies. But the problem is that you don't have enough cookies to use up all the sandwiches. You have only 16 cookies to use up, all right? So therefore, you won't be able to use up all the sandwiches if you have only 16 cookies. On the other hand, if you look at things from the perspective of the oranges, again, there's a 1-to-2 ratio between the orange and the cookies. In this case, you have 10 oranges, which means that you're going to need 20 cookies. Again, you don't have enough cookies to use up all the oranges. Now, if you look at things from the standpoint of the cookies, based on the equation here, for 16 cookies, you're going to need 8 sandwiches and 8 oranges. So it turns out that you have enough sandwiches and enough cookies to use up, enough sandwiches and enough oranges to use up all the cookies, all right? So basically what's going to happen is that all the cookies will be used up. 8 of the 11 sandwiches would be used up, leaving behind 3, and 8 of the 10 oranges would be used up, leaving behind 2, all right? So therefore, the cookies would be what we call the limiting items, because basically the amount of packaged meals that you can get is limited by the amount of cookies that is present, given the numbers of oranges and sandwiches that are also present, all right? And this is the whole idea behind the limiting reactant concept. Basically, if you have more than 1 reactant present, then the limiting reactant is the one that will be totally used up, and it will be the reactant that will determine how much of the products you expect to get. Just as the 16 cookies here is a limiting item that determines ultimately how many meals you can put together based on 16 cookies, 11 sandwiches, and 10 oranges, all right? So the cookies would be the limiting item, while the oranges and the sandwiches would be the items in excess. And we have a similar terminology when it comes to chemical reactions, where the limiting reactant is the one that is totally used up, and the other items or the other reactants would be the excess reactants, all right? And we're going to see that actual example, an actual chemistry example of this idea. But before we do that, let's look at, again, using the example that we saw on the previous slide. Let's see if we can use that to answer the question. How many meals can be made from 105 sandwiches, 202 cookies, and 107 oranges? So a simple way of going about solving this problem is that we basically take each item and then try to determine how many meals can be based from or based on each item. So in the case of the sandwiches, there's a 1-to-1 ratio between a sandwich and a meal. So based on the sandwiches only, you can get 105 meals. Based on the cookies only, because of the 1-to-2 ratio, get 101 meals. And then finally, in the case of the oranges, 1-to-1 ratio between the meal and orange. So therefore you expect to get 107 meals based on the oranges only. Of course, we know that one of these items would be the limiting item. And basically the one that would be the limiting item in this case, I'm sorry, will be the cookies, because based on these calculations that we just did, the lowest amount of meals that can be calculated based on each of these three would be the 101 meals coming from the 202 cookies. So therefore, this is how we can determine which item is a limiting item. Just basically, we calculate based on each of these items, how many products you expect to get. In this case, meals you expect to get. So therefore, again, the cookies would be the limiting item, and the sandwiches and the oranges would be the items in excess, all right? So that's how you determine which item is limiting. So with that out of the way, let's move on now to an actual chemistry example. So in this example, hold on 1 minute. Okay, so in this example, they gave you some information about magnesium nitride, and it said magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. And the A part is asking how many grams of magnesium nitride can be made in the reaction of 35.0 grams of magnesium and 15.0 grams of nitrogen. And then the B part is asking how many grams of the excess reactant remain after the reaction. Okay, so this is a typical stoichiometric type problem where basically you have to first write down the balanced equation, and then you have to write down, or determine, I should say, which of the reactants would be the limiting reactants, right? Because they gave you a certain amount of each reactant. And based on the limiting reactant, you can determine how much of the product you expect to get. Okay, so that's basically what you need to do for the A part. Now the B part, I'm going to explain how to determine the amount of excess reactant. Okay, so let me get out of this here. And let me go here. Okay, so first thing we need to do is write down the balanced equation for the reaction. So the question says magnesium nitride can be formed by the reaction of magnesium metal. Okay, so I'm going to write down the formula for magnesium. All right, plus nitrogen. And you should remember that nitrogen, which is a gas, exists as N2. Remember, there are certain gases that exist as diatomic gases. Let me remind you of what those gases are. They are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. All right. So those are the elements that exist as diatomic molecules. So whenever you see a question talking about any one of these elements in nature, then you know that the formula would be written as a diatomic molecule. So in the case of nitrogen, it is N2, all right? So the next step is determine what the product is, or actually one product. And the question says that the product is magnesium nitride. Now, can anybody tell me what the formula for magnesium nitride is? What is the formula for magnesium nitride? Now, in order to answer this, you may need to consult the tables I provided for you, all right? Remember, the tables gives you a list of common ions. So what you would do is look up the formula for the magnesium ion and the formula for the nitride ion. So let's do this over here. What's the formula for the magnesium ion? Anybody?
Mg.
Well, that's part of it. What's the charge? Mg2+, okay. And what's the formula for the nitride ion?
And
Anybody?
-3.
And what?
-3.
Or, okay, or 3-, same thing.
Yeah.
Okay, so how would you determine the formula for the compound formed from these two ions?
Multiply the Mg times 3 and the N times 2.
All right, so this will be multiplied by 3, and this will be multiplied by 2. So what would be the final formula for magnesium nitride?
Mg3N2.
Mg3N2. So as you can see, it's very important that you know how to write down the formula for a compound like this. So let me write that here, Mg3N2. The next step is that we need to balance this equation. So how would you balance this equation?
Three on the magnesium, 1 on
Okay.
the
Okay, so
nitrogen.
put a
and
3
then-
magnesium here,
Yeah.
and that's pretty much it. You don't need to do anything else, all
Yeah.
right? Okay, very good. So this is very important as well. The balanced equation, very important. Okay, so let's move on now to the calculation part. So the question says, how many grams of magnesium nitride can be made in the reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen? So what I'm going to do is start out with the 35.00 grams of magnesium, all right? And what I'm going to do is calculate the moles of the product. So the first step would be to convert from grams of magnesium to moles of magnesium. So 1 mole of Mg would be up top, 24.31 grams of magnesium would be at the bottom, because that would be the molar mass of magnesium. So that's 24. Okay, so this unit, grams of magnesium, will cancel out with the grams of magnesium here. The next step is the mole ratio between the magnesium and the magnesium nitride. And you'll notice that there's a 1 here for the magnesium nitride, and over here, there's a 3 here, all right? So the way we represent that here would be that you have 3 moles of magnesium down here as the denominator, and 1 mole of magnesium nitride up top as the numerator. And let me work that out. So 35 divided by 24.31. And then we divide by 3. So according to my calculation, this works out to be equal to 0.4799 moles of Mg3N2, all right? And then we do something similar with the 15.0 grams, 00 grams, I'm sorry, of 15.00 grams of nitrogen multiplied by the molar mass, or divide by the molar mass, I'm sorry, 1 mole of N2. Okay, so nitrogen, the molar mass is 14.01 for 1 atom, so multiply by 2, that will give you 28.02 grams of nitrogen, all right? And then we go from there to the moles of the product. So 1 mole of Mg3N2 up top, and 1 mole of N2 below. So this will go with that. This will go with that. And then we do our number crunching. So 15 divided by 28.02 and multiplied by 1 gives you, according to my calculations, 0.53 0.53 moles of Mg 3 and 2. Okay, so at this juncture, we can tell which reactant is limiting. Why? Because when you compare this number to this number, this one is lower. So let me put here, this one is lower, which means that the magnesium here would be the limiting reactant. All right. So to answer the question, how many grams of magnesium nitride would be made? What we have to do is convert this moles to grams. So let me do that right here. So you're going to have 1 mole of Mg 3N2. Let me erase this here. Okay. And above as the numerator, we're going to put the molar mass of magnesium nitride. Let me see if I can find that out here. So molar. Okay, so Mg 3 and 2. And let's see what this gives. Okay, so according to this, the molar mass of magnesium nitride is 100.93 grams of Mg 3 and 2. Okay, so when I work this out, so 0.4799 multiplied by 0.5353. Okay, so when I work this out, the answer I got is 0. How many sig figs? 4 sig figs. 0.2569. No, something is wrong here. I did something wrong. I'm sorry. I'm gonna do this again. 0.4799 multiplied by 100.93. I don't know what I was doing. So this gives you 48.44. So we'll go over here. Grab the eraser. Go back here and get this. Okay, so the answer for this part here is, okay, where is this pen? Okay. 48.44 grams of Mg 3 and 2. Okay, so this is the answer for the A part of the question. All right. Okay. Any questions about this? Any questions about the A part? Any questions? Okay, now for the B part, let's go back to the PowerPoint here to follow what's happening in the B part. In the B part, the question says, how many grams of the excess reactant remain after the reaction, all right? Now remember, once you identify a reactant as a limiting reactant, that means that all other reactants will be the excess reactant. So going back to what I wrote down here, we know that the magnesium is the limiting reactant. Remember, we made that point here. So that means that the nitrogen would be the limiting reactant. So what the question is asking for is how much by way of grams nitrogen would be remaining. Now, how do we determine that? Well, the first thing we need to do, so this here is for the B part. This was the A part here. Okay, so what we need to do is start off with the limiting reactant, 35.00 grams of magnesium. And we convert it to moles like we did before. So 1 mole of magnesium above and 24.31 grams of magnesium below. Whoops. And then we look at the mole ratio between the limiting reactant and the excess reactant, right? And based on the equation here, it's a 3-to-1 ratio between the magnesium, which is the limiting reactant, and the nitrogen, which is the excess reactant. So therefore, we're going to put 3 moles of magnesium down here and 1 mole of nitrogen above. And then the next step is to convert the moles to grams. So we're going to have 1 mole of nitrogen down here and 28.02 grams of nitrogen N2 above, so that this will cancel out with this will cancel out with that, this will cancel out with that. So the only thing that will remain will be the grams of nitrogen. That's the only unit remaining here. So let's do our number crunching. So we start off with 35.00 divided by 24.31 divided by 3 times 28.02. And according to my calculations, this works out to be equal to 13.45. So 13.45 grams of nitrogen. Now remember, this is the mass of nitrogen that reacted, all right? But what the question is asking for is the mass of nitrogen that remains, right? So according to the question, the amount of nitrogen that we had initially is 15 grams. 15 grams, 15.00 grams. So this is the amount that was there originally. And then the amount that reacted would be 13.45 grams, which means that the amount remaining would be 15.00 minus 13.45, and that would be equal to 1.55 grams. So let me, 1.55 grams. So that would be the answer to the B part. Okay, any questions about this? Any questions? Any questions about this example? Okay, so let's move on. Let's talk about this concept of yields. And again, this is something that you should have met before. All right, and this is something that you need to understand, because unlike what we would like to have in an ideal world, very often the amount of product that you expect to get would not be what you actually get if you conduct the experiment or the reaction to get the product, all right? So for example, going back to the example that we were just looking at, the example suggests, let me go back to this one here, that you'd expect to get 48.44 grams of magnesium nitride, right, based on the calculations that we did here. But what you'll find in practice is the amount of product that you get would be less than the 48.44 grams, all right? And there are many reasons why that is the case, all right? As stated down here, hold on 1 minute. As stated down here, there may be errors in the experiment, maybe poor techniques. Sometimes the reactions are reversible, and sometimes you have what are called competing reactions, where you have 2 reactions from the same reactants occurring at the same time. So all these things can basically reduce the amount of product you expect to get. So therefore, it's very important that we express what is known as the theoretical yield, and then the actual yield, and then the percent yield. So the theoretical yield, the definition is given here. The theoretical yield is the amount of product you expect to get based on the stoichiometry and the calculations that you'd have done, all right? So that's basically what the theoretical yield is. So the example that we did before, when we calculated the amount of magnesium nitride, that is the theoretical yield, all right? Now the actual yield is the amount of product that is produced in the reaction itself. So if somebody did the reaction and they end up with a certain amount of product, then that amount of product would be the actual yield. And as stated here, in practice, in the vast majority of cases, the actual yield is less than the theoretical yield. In practice, if you do a reaction and you get above 90%, you're doing very good in terms of the percent yield, because very often percent yields in practice are like 50% and below, all right? Okay, so the relationship between the actual and the theoretical yield is given as a ratio, as shown here, and that is called the percent yield, right? So the percent yield is the actual divided by the theoretical times 100%. And the percent yield is basically what is quoted as a measure of how successful the reaction is. And if you look in any chemical literature, even the most advanced or prestigious chemical literature, you'll find that whenever a reaction is producing a product, among the other things that is quoted would be the percent yield, right? So you'll see mentioned that, for example, a particular reaction gives a 65% yield, and so on and so forth, all right? So that's the relationship between the actual and the theoretical yield. Actual divided by the theoretical will give you the percent yield, which is expressed as a percentage. Okay, let's see here. Let me see if I can find an example of a percent yield problem for us to do. So let me go back to okay, let's see here. Okay, let's do this one here. Okay, let me, oh, you know what, let me do it piecemeal. Okay. Oh. All right. Oh no. Let me go back to this. And then, all right. Seems as if I'm having a problem here with copy and paste. Okay, for some reason I can't copy and paste this. And I cannot write on this. Okay, what I'm going to do is I'm going to come up with some examples of percent yield problems, and then I'm just going to do that in the next class, all right? In the meantime, let's continue our discussion of, or continue to our discussion of solutions and concentrations, right? Now, you should know, or you all should know what the definition of a solution is. A solution is basically a homogeneous mixture of two or more substances. Now, what we'll be talking about in this section are aqueous solutions, all right? So you should know that there are two parts to the solution. You have the solute and you have the solvent, right? And basically the solute is a substance that is being dissolved, and the solvent is a substance that is doing the dissolving, all right? Now, you can have a situation where the solutes and solvents are in the same phase or they're in different phases. I won't go through all the examples. But in the case of water, water is usually a solvent in these situations, and the other substance, which could be a solid or liquid or gas, would be the solute, all right? So for example, a solution of sodium chloride, in that case, the solvent would be water and the sodium chloride would be the solute. Okay, let me get rid of this person here. Sorry about that. Okay, so let's talk about concentration. So the concentration of a solution can be expressed in different ways. It's basically a measure of the amount of solute per unit of solvent, all right? So one way of expressing concentration is what you see here. It's called the molarity. And by definition, a molarity is the moles of solute divided by the liters of solution, right? So we call that the molar concentration, which is the amount of solute per liter of solution. There are other ways of expressing concentration, which we'll see later on. But for now, this is what we're going to use in this chapter, all right? So here we can make a distinction between a solution which is dilute and one that is concentrated. And these are relative terms, all right? So in this case here, oh, by the way, before I do that, I forgot to mention one thing. So the units of molarity can be expressed in two ways. The unit of molarity can be expressed as, sorry. Okay, so the unit of molarity can be expressed as moles per liter or uppercase M, as you can see here, all right? So if you see this, it means the same thing as this, all right? Okay, so with that out of the way, just to give you a couple of examples. So in this case here, this solution is more dilute because as you can see here, let me get back my pointer. As you can see here in this solution, it is made up of 0.05 moles of sodium chloride dissolved in 500 mils of water. So if you divide 0.05 by 500, you're going to get 0.1 M or 0.1 mole per liter. So this is the more dilute solution when compared to this one, because in the case of this one, it is a 5 mole of sodium chloride dissolved in 1 liter of solution in this case here. So therefore, this solution here is more concentrated compared to this solution. And if you could actually see the particles of the solute, you'll see that the particles here would be on average closer to each other in the case of the more concentrated solution compared to the more dilute solution. All right, so that basically is showing you the difference between a more dilute solution compared to a more concentrated solution. Okay, so with that example, what I'm going to do is, okay, I'm going to take a break here, and then when we get back, we're going to look at these examples, and then I think we'll call it a day. Let me just check something here. We may discuss dilutions shortly after covering these examples. So it's now 11:48. We're going to restart at 12 o'clock. All right, so I'll be back. Okay, so can you hear me now?
Yes.
Okay,
Yes.
good. All right, so let's talk about these examples. And these examples are based on what we just covered. Okay, so let's deal with number one first. Number one says, how would you prepare a 500 ml of a 0.250 m solution of sodium phosphate? Okay, so. Oh, whoops. I need to. Excuse me 1 minute.
Yes.
Okay, good. All right, so let's talk about these examples. Okay. Sorry about that. All right, so let me get out of this here. We're going to do number one first. And let me open this up. Let me clean this up. All right, so basic information given in this question are the volume, which is 500 mils of the solution, and the molarity, which is 0.250 m. All right. Now, what we need to find out is the amount of the solute, which is sodium phosphate. So let me write the formula down. Na3PO4, that is the solute. All right. So basically we need to find the mass of the solute. So what we're going to do is start off with the volume, which is 500 mils, convert it to liters. So you're going to have 1 liter here, 1,000 mils above. And then the next conversion factor would be the molarity expressed as a conversion factor, which would be 0.250 moles over 1 liter. And then the next step is that we need to convert from moles to grams. So that means we need the molar mass of the sodium phosphate. Let me see if I can find that here. Na3PO4. Na3PO4. Okay, why is this thing not budging? Na3. Okay, I don't know what's going on here with this thing. So let me refresh this page. Okay. Oh, okay. Na3PO4. Okay, 163.94 grams per mole. So we're going to put 163.94 grams over 1 mole. All right, so the mils will cancel out here and here. The liters will cancel out here and here. The moles will cancel there and there, all right? So let's do our number crunching. So 500 divided by 1,000 times 0.250 times 163.94. And according to my calculation, this works out to be equal to 20.5, 366. So 20.5 grams, all right? So that would be the mass of the sodium phosphate that you would need to weigh. Now, we're not finished with answering the question yet, because you'll notice the question says, let me go back to the PowerPoint. How would you prepare the solution, right? So basically what you need to do is describe how you prepare the solution. So you have to write a statement after doing the calculations. So your statement should be a short statement, nothing fancy. It should say something like this. I would weigh 20.5 grams of Na3PO4 and add water to make a final solution of 0.250 M. And that would complete the answer to this question. All right. And I want to point out something here. It's very important that you understand this. Look at how the question, look at how the answer is worded. What I said here is that I would first weigh 20.5 grams of the solute and then add water to it, and not the other way around. In other words, you don't measure. Oh, by the way, I just realized something. I forgot one thing here. I would add 500 mils of water. Very important. All right. Okay, so as I was saying, please note how this is worded, right? What you do is weigh 20.5 grams of the sodium phosphate, and then you add, oh gosh, I made another mistake. I'm so sorry, folks. Let me erase this here. I'm sorry. Because the wording is very important. That's why I'm making sure I'm doing this right. Okay, so go back to this. All right. To make a final solution, oops, of 500 mils of 0.250 M. Okay? All right, so let me just say this now. So please note how this is worded. I'm weighing 20.5 grams of the solute, and then I add water until you get to a final volume of 500 mils, all right? And that's basically how you make up solutions like these, all right? Now, what would be incorrect is actually what I had before, in that you add 500 mils of water to 20.5 mils of the solute. That would be incorrect. And the reason why that would be incorrect is because if you do it that way, there's no guarantee that the final volume is going to be 500 mils. The 500 mils or the final volume might be greater or less than 500 mils if you add it after. If you add the volume required after. So what you do is weigh your solute first and then add your water until you get to a final solution. And in fact, I think I have some photographs here which shows you the type of glassware that we use. Let me see if I can find it. Okay, so this is the glassware that is used here. We're going to talk about this in relation to dilution as well, but I'll mention it here. We call this a volumetric flask. They come in different sizes, but they're very accurately made and they're designed to measure a particular volume. So for example, in our exercise or our example that we did here, we would need a flask, a volumetric flask, which has a volume of 500 mils, all right? That would be the flask that we would use. And if you look at the flask closely, let me see if it's here. Well, it's not here, but in fact, let me pull up a picture of a volumetric flask because I think it's important that you see what it looks like. And for those of you enrolled in my lab class, you'll be working with such a flask in the next lab period. So let me see if I can find a picture of it. Volumetric flask. Okay, so we have a couple of pictures here. And these are companies that sell these pieces of glassware. I want to find a good one. So you can see, okay, let's look at this one here. Okay, but I cannot see the mark on it. All right, let me try to explain. Okay, so this is a volumetric flask, which is sold by this company called Norchemist. And basically, as I said before, it's very accurately made. There's a, whoops, oh, I have a close-up here. Okay, if you look at this closely, I don't know if you can see it on your screen, right? This part of the flask is magnified. There is a mark that is etched right here, right, on the stem of the flask. That represents the volume of that flask if you add liquid up to that mark, all right? So this particular flask is, let me see what kind of flask, what volume. It's a 250 ml flask, right? So basically, if you add a liquid up to that mark, then you know that your liquid has a volume of 250. And in fact, it's accurate to 2 decimal places. So it would be 250.00 mils, all right? So that's the kind of flask that you would use to make solutions of the type that we were talking about in this example. And based on the calculation here, the flask that we would use is a 500 ml flask, all right? So that's basically how we would make a solution of a specific concentration. Okay, let's go back to the next question. It says, in an experiment, 15.0 grams of sodium hydroxide completely neutralizes 125 mils of phosphoric acid. So the first question is, write a balanced equation for the reaction between the two reactants. Now, if you remember in, I think earlier in this chapter actually, we talked about the acid-base reaction, right? And you should recognize that sodium hydroxide is a base and the phosphoric acid is an acid, all right? So we know that an acid and a base will react to form a salt and water. So let me write down the formula for the sodium hydroxide here. And the phosphoric acid, which is H3PO4, all right? So can anybody tell me what the products of this reaction is going to be? Neutralization reaction. Or what's the product of any neutralization reaction? Anybody? Come on, you should be able to answer this one because we just talked about it, I think on Wednesday or Monday, I don't remember, but it was last week. Well,
Water.
okay, that's one of the two products. So let me put that here. And what's the other product?
Sodium phosphate.
Okay, and what's the formula for sodium phosphate?
Na3PO4.
Very good. Na3PO4. Very good. So the next step is that we need to balance this equation. So how would you go about balancing this equation? It should be A here. Well,
Put a 3 on the sodium hydroxide.
okay, so put a 3 here. Anything else?
Would you put a 2 on the water?
No, that won't balance.
Oh,
You need to put something there, but not 2. Well, let's look at the hydrogens. How many hydrogens total do we have on the left side?
6.
Okay, so what do you think you should do here?
3.
Exactly, put a 3 here. And that will balance the oxygens as well because you have 7 oxygens on both sides, all right? Okay, so we needed to get that out of the way in order to answer, let me go back to the PowerPoint here, in order to answer the A part. Now the B part is asking for the molarity of the sodium phosphate solution. So how do we do that? Well, they gave us 15.0 grams. Let me write this down here. They gave us 15.0 grams of sodium hydroxide. So what I would do is convert this to moles. And we do that by multiplying by 1 mole of sodium hydroxide over the molar mass, which is 40.00 grams of sodium hydroxide, all right? So that this will cancel with this. And then the next step would be the mole ratio between the phosphoric acid and the sodium hydroxide, which is the reason why you needed to balance the equation, because you want to make sure that you have the correct coefficients for the substances involved. So the way we would represent that in this conversion factor is that I'm going to put 3 moles of sodium hydroxide down here and 1 mole of H3PO4 above. All right. Now that gives us the moles of phosphoric acid. Hey, this is just a temporary thing right now. What?
Okay, they moved me up here.
Oh, really? I'm sorry.
No, that's okay. I can check another room, but I might have students popping in here shortly.
Oh, okay.
'Cause they just-
I'll be finished in the next 20 minutes.
Okay.
If that's fine.
Yeah, 12:30 is when it starts.
Oh, okay. I'll finish before then.
Okay, I'm sorry.
Yeah, no problem.
They told me.
Okay, guys, I'm sorry about that. Okay, where was I? Okay, so this is going to cancel out with that. So up to this point, we would have determined the moles of phosphoric acid. But remember, the question is asking for the molarity of phosphoric acid. So once we get the moles, we divide that by the volume in liters. Now, they gave us 125 mils of phosphoric acid, H3PO4. What we need to do is convert that to liters. So we're going to have 1 liter of H3PO4 above, and 1,000 mils of H3PO4 below. All right, so this is going to cancel with this. So your final answer will be expressed in moles, moles per liter. All right, so let's do the number crunching. 15 divided by 40 divided by 3, and then divided by 125. 1,000. Okay, so according to my calculations, this works out to be equal to, okay, where is that? 1.00 mole per liter. All right, so that basically answers the A part. Okay, so let me put here the A part here. So for the B part, it's asking what is the concentration in grams per dm cube. So we have 1.00 moles per liter, and they're asking for you to convert it to grams per dm cube. All right. So what you can do is you can convert from moles to grams and then from liters to dm cube. So let me show you how to do that down here. So 1.00 moles per liter. What I'm going to do is convert from liters to dm cube. And if you look in the tables, you'll see that 1 liter is equal to 1 dm cube. All right. And then we convert from moles to grams, which means you need the molar mass of phosphoric acid. Let me see if I can find it here. Okay, so according to my calculations, the molar mass of phosphoric acid is 98.00 grams per mole, 1 mole. So this unit will cancel out with that unit. So therefore the answer will become 98.00 grams per dm cube. So that answers the B part, all right? And then for the C part, the question is asking for the concentration in milligrams per milliliters, milligrams per milliliters. And in fact, I can do it here. It doesn't take up much space to do that here. So basically, you're going to start off with 98.00 grams per dm cube. Well, to convert from grams to milligrams, it's going to be 1,000 milligrams over 1 gram. And to convert from dm cube to milliliters, you're going to have 1 dm cube above, 1,000 mils below. And what you'll find is that not only will you have the gram units canceling out and the dm cube units canceling out, but this 1,000 here will cancel out with the 1,000 here. So basically the numerical answer would be the same, which would be 98.00 milligrams per milliliters. And that's how that is done, all right? Okay, I'm going to stop here for today since my colleague wants to use this classroom. So any particular questions I can answer quickly, or if you want to, you can ask me those questions during office hours tomorrow or any other time that we can meet. So any questions? No questions? Okay, well, if that's it for today then. So enjoy the rest of your day. And I'll see some of you later, I think, in lab. So until then, take care.